So we've already talked about how you find vertical and horizontal asymptotes of rational functions, and how you find the x-intercept and the y-intercept. And this information kind of gives you a general idea of what might happen in a graph. So let's go and find this same information for r of x equals 5x plus 21 over x squared plus 10x plus 25. So the vertical asymptote is what you get when you set the denominator equal to 0. Well, when you set the denominator equal to 0, you got one of two options. You're either going to graph it and find the solutions, or you're going to factor it and solve for x. Either way, you're going to find out that the vertical asymptote is negative 5. So there's only one vertical asymptote. Now let's go find the horizontal asymptote. Well, look at the biggest exponent of x, which is x squared. It only occurs in the denominator. That means that this is your y-intercept. I'm sorry, it's your horizontal asymptote. Now let's go find our x-intercept. The x-intercept you find by setting the numerator equal to 0 and solving. So x is negative 21 over 5. Well, negative 21 over 5 is like negative 4.2. So 1, 2, 3, 4. So there's an x-intercept over here. And then the y-intercept is what you get when you make all the x's zeros. You're left with 21 over 25. Well, 21 over 25 is like 0.84. So we're going to find out that the graph looks like this. But then the other part of it is kind of weird. It looks kind of like this. So it crosses over our horizontal asymptote, but then the graph kind of comes back down and gets close to that horizontal asymptote again. Alright, let's do this again, but this time I'm going to talk a little bit about how you determine the end behavior near the asymptotes. So sometimes one of the best ways of starting these problems is factoring everything if you can. Remember, not all these polynomials can be factored. Well, it just so happens the numerator can be factored into x minus 4x plus 1. And the denominator, you can take out a 2x, and you're left with x plus 2. Alright, so everything's factored. So let's start with the vertical asymptote, which is going to be x equals 0 and x equals negative 2. So there are two vertical asymptotes. One at 0 and one at negative 2. Now I'm going to go to the horizontal asymptote. In order to find that, I look back at the original problem. The biggest exponent of x in the numerator and denominator is the same, so the vertical asymptote is the ratio of the coefficients, so it's 1/2. So make that 1, 1/2 is right here. The x-intercept is when the numerator is equal to 0. Well, when the numerator is equal to 0, I find out the x-intercepts are at 4 and negative 1. So I know it hits here and here. And then the y-intercept is what happens when you plug in x's or zeros everywhere there's an x. Wait a second. When I do that, I don't have anything left in the denominator, do I? That means there must not be a y-intercept. And that can happen. Remember that the y-axis is one of our asymptotes. So that's why there is no y-intercept. Alright, so now let's go talk about what happens close to the asymptotes. If you want to know where the graph is going, if it's going up or down, one of the things you can do is pick a value of x that's close to it, or what's happening as you're approaching from one side or the other. So one of our vertical asymptotes is at negative 2, so let's use negative 3 as a for example. What happens when I plug -3 back into the original problem? But let's plug it into the factored form. All right, so if you plug -3 in, you get a negative times a negative all over a negative times a negative. Well, two negatives make a positive over a positive is a positive. That means that at -3, the graph is approaching positive infinity. That means the graph went up over here. Well, it must go this way. The reason I know that is because it's not going to cross the horizontal asymptote at this point. Okay, now let's find out what happens to the graph between -2 and 0. So, let's try, let's see, what would be a good number to try? So you already know that at x is -1, that the answer is 0. So we probably need to try something else. So maybe we'll try, let's see, -1.5. So at -1.5, if I plug that in, I get a negative times a negative over a negative times a positive. Well, what's going to happen? You get a positive over a negative, which is going to give you a negative, which means the graph is going to negative infinity. So it must be down here somewhere. Now let's try -1/2 and see what happens. Well, if I plug in -1/2 back into that factored form above, I get a negative times a positive over a negative times a positive. Well, that's a negative over a negative, which is a positive, which means it goes to positive infinity, which means this part of the graph goes up. So this is one of those cases where part of the graph actually does cross the horizontal asymptote. All right, now let's go find out what happens to the graph over to the right of the x = 0 asymptote. So let's try 1 because it's the easiest one to use. So if I plug, let's make that look nicer. If I plug 1 in, I get a negative times a positive over a positive times a positive. Well, that's going to be negative, which means that the graph must be doing this. And we said that it crosses the x-axis at 4, so it must be doing something more like that. And that's what the graph looks like without me ever plugging it into the graphing calculator. There is one other type of asymptote which will occur when we're graphing rational functions. It is called the slant asymptote. Most of our asymptotes have been horizontal or vertical, and sometimes we have a diagonal asymptote. Like the vertical and horizontal asymptotes, the slant asymptote is going to be linear. It's going to be a straight line. It's just going to be slanted, so you're going to get kind of a more slanty graph than you're used to. In this example, r of x equals x squared minus 4x minus 5 over x minus 3, I want you to notice that the degree of the numerator is exactly 1 more than the degree of the denominator. So to find a slant asymptote, we're going to go back to our favorite longhand polynomial division. Never thought it would be so useful, did you? All right, so we want to find out how many times x minus 3 goes into x squared minus 4x, and it goes in x. So I multiply the divisor by x, and I get x squared minus 3x. I subtract, these go away. Negative 4x minus negative 3x is negative x, bring down the minus 5. How many times does x minus 3 go into negative x minus 5? Negative 1. And at this point in time I can stop, because the slant asymptote is just the linear equation that you're going to get in the quotient of your division problem. The remainder means nothing. The other thing is the vertical asymptote, what you get when you set the denominator equal to 0 is going to be 3. So if I were to go and draw a quick sketch, I would have vertical asymptote here, and the slant asymptote has a y-intercept of -5, and it goes down 1 to the right 1. or up one to the left one. So it's going to kind of look like this. I guess I didn't give myself as much space as I probably should have. Alright, so now let's go back and look at this again. There's no horizontal asymptote because the bigger exponent of x is in the numerator. It's one of the reasons there's a slant asymptote. The x-intercepts, however, are where the numerator is equal to 0. Should make that look more like a 5. Well, this one's easy. It factors into x minus 5x plus 1. So the x-intercepts must be at 5 and negative 1. So there's one here and one here. We can kind of do the same thing to find out what the end behavior is going to look like. And then you got to tell me that I did my slant asymptote wrong. I've got the right equation, except that it should have gone up one to the right one. Instead of down one to the right one. All right, now that should work out a little bit better. Except for I'm still having problems here. Let's try this one more time. I'm not sure where I'm even getting my numbers from tonight. Maybe it's because I'm tired. I have no idea who I am. All right, let's see. The slant asymptote is x minus 1. Here's 1. Up one to the right one, up one to the right one, up one to the right one. Now I think I have a little bit better idea of where my slant asymptote's at. Okay, now that's fine. Now, you can find the end behavior, or you can kind of figure that what's going to happen is, since the x-intercept is at negative 1, that part of the graph is going to look like that. The other part of the graph is going to look, I know it doesn't look so well here, but if you graph it on your calculator, it'll look a lot nicer and curvier than the one that I just drew. It's going to look something along those lines. A practical application of rational functions occurs in the theory of electricity when two resistors are connected in parallel, R1 and R2. Their combined resistance R is given by the formula R1 times R2 over R1 plus R2. Suppose that a fixed 8 ohm resistor is connected in parallel with a variable resistor. The variable resistor, we're going to call it X. If the resistance of the variable resistor is denoted by X and combined with resistance, or is combined with the 8 ohm resistor, we would like to know what the graph of this function would look like. Well, first I'm going to go plug in 8 and X. Turns out that this rational function is 8x over 8 plus x. The vertical asymptote is going to be x equals negative 8. But here's the deal. You can't have negative resistance, so that vertical asymptote of negative 8 doesn't mean anything. The horizontal asymptote is going to be y equals 8. So here's y equals 8. If you plug in 0 for x, the resistance is going to start at 0. And then as you increase x, you're increasing the combined resistance. Except that horizontal asymptote says that the graph is going to continuously get closer to it, but never actually touch it. So you can keep getting close to 8 ohms, but you're not actually going to reach it.